Hey, welcome back, everybody. Well, the three of you at least. Class is getting a little smaller. Anyway, what I wanted to do is I forgot to show you a, oh, by the way, the exam is, I graded all of it, and you should take a look. I will open up the exam so you can look at the correct answers. But I have to coordinate that with the coordinator because they open it up at one day or one time. I forget how long. So they haven't sent me anything yet. But as soon as I find out, I'll let you know. So you can use that to help you study for the final. Okay. Any questions, comments, concerns? We're currently on chapter 8. What I want to do is kind of go back because we were talking about this in chapter 7, dealing with polarity. And there is a resource that I have on the course website that you should take a look at and help you to grasp the concept of polarity. Now, if you go under modules, and you scroll down, there should be a module labeled Additional Chemistry Resources as follows. Select the molecular polarity, okay? And when you click on that, there's a link. When you click on the link, it will send you to the simulation, which is as follows, okay? So you have a couple of choices. Here you can talk about, let me click the link and get to the opening menu. So you have a couple of choices here to deal with different topics of polarity. You can do just a 2-atom A-B scenario or a 3-atom scenario and actually see real world molecules, okay? But just to understand the concept of polarity in a bond, just select the 2-atom choice. So when you click that, what's going to happen is you're going to see atom A and atom B. Take the arrow, move both of them to the same position. So therefore, what this shows is you have atom A and atom B, which is basically the same atom. I wish they would have made it 2 A's or 2 B's. But if you select up on top here, the partial charges, okay, the delta notation, and electrostatic potential. Now, what that shows is the following. There's a color scale on top. Blue represents a positive character, and red represents a negative charge character. Obviously, as you progress, it's a progression, it's a gradient. So you go from a light red, for example, to a dark red, and the same is true for the blue, okay? So let's just begin with partial charges on, electrostatic potential on. You can do electron density, but what that does is like a grayscale picture. Maybe it's a little bit tougher to see, but I prefer the electrostatic potential, and I see the color here. Okay, now grab any of the atoms, A or B. I'm gonna take the slide here for B, and I'm gonna move it over, grab it, and select it, and just drag it over to the right. Notice the electrostatic potential on B starts to get red in color, and on the A side becomes blue. We're also starting to create the dipole arrow. Okay, we call that dipole arrow, where the arrow points to the electronegative charge, and the tail points to the partial positive. Okay. I should say electronegative, partial negative, which is the red side, and partial positive, which is the blue side. So let's grab it again. We start moving B over to the far right, because what's happening there is the electronegativity is increasing. In other words, maybe I select a different element that has a higher electronegativity. And this could be, this could be 2 carbons, for example, bonded together, A and B. Notice equal pull in that bond, it's a covalent bond, equal pull. And then maybe B, I can switch it over to, let's say, nitrogen. So now I got a carbon-nitrogen bond. And I know that obviously nitrogen is a lot more electronegative than carbon. Therefore, it has a higher En, which means it's pulling the electron density onto the cell. And the arrow is pointing to B, which represents, in this case, nitrogen. Okay. So that gives you that scenario. We can put an electric field about on this. If you notice, we have a plate on the right with a positive charge, plate and a left negative charge. And if I grab that molecule, just move it around, the B side, the partial negative side, is going to be attracted to the positive plate of the electric field, and it lines up real nice. Okay, so that gives you an idea about polarity, which is related to the electronegativity. Okay, now let's say I put B about right there, and what happens with A, if I increase its electronegativity, I'm back to a dipole, a no dipole, and a nonpolar molecule. This represents a polar molecule because I have a dipole, and this represents a nonpolar molecule because the electronegativity of both A and B in this example is the same. Okay, so use that as to give you an idea, a better understanding on polarity. We can, for example, let's go back and select real molecules. Uh-oh, what happened there? Oh, it's not currently available because they're converting some of these into the new HTML format 5, and it's not ready. Let's see this one. So here's another one where it's 3 molecules. You can play with electronegativity and so forth. And just give you a better idea how things, a better picture of electronegativity and how it's related to polarity of the bond. Okay, and eventually the molecule. All right, so any questions about that? Just an additional resource for you. Okay, we ended up on slide 4 of the chapter dealing with the next chapter. And verify that, yeah, chapter 8, we were on slide 4. And I just introduced the idea of oxidation state, which in the past I've been using the term the charge, either have a positive charge or a negative charge. Well, I'm going to start using now the term oxidation state because that's more descriptive of what's going on with respect to ionic compounds versus covalent compounds. Ionic compounds, there's no question, there's a full charge on the cation and a full charge in the anion. So we can literally talk about a charge. Now, with respect to covalent compounds, there is not a full charge. There's a partial charge denoted by the delta location. And so it's kind of ambiguous if you think about it between the two. And so what is the term that is used to describe the charge, be it an ionic compound or be it a covalent compound, it is oxidation number, okay? So everybody in group 1 has an oxidation number of a +1. That's the only difference. In group 2, oxidation number of a +2. Now, the elements, as I stated countless of times, a lot of times I sound redundant, but it's for a reason, okay? All elements have a net oxidation state of 0, okay? Because they have an equal number of protons and an equal number of electrons. It is when they lose or gain electrons that their oxidation number changes, their oxidation state, which puts them into a plus category or a negative category, okay? Now we had fixed charges. Now I don't recall if I went over this. There are 16 elements that have what are called fixed charges. I'm going to rehash that just to make sure we're in the same boat. I'm going to bring up the periodic table that I have here marked. You can see that the ones that I have circled in red are these elements have a fixed charge. And that's important when it comes to naming compounds, because when they don't have a fixed charge, we have to use Roman numerals to distinguish between which one we're talking about. All right, so everybody in group 1, all the metals, not excluding hydrogen, obviously, right? Because it's not a metal. All the metals in group 1 always 100% of the time have a +1 charge when they become an oxidation state of a +1, when they become an ions. Everybody that's a +1, +2 oxidation state for everybody in group 2A, all the metals. Now that's a total of 12 elements that have a fixed charge 100% of the time. Now we're going to add four more metals that have a fixed charge, a fixed oxidation state. And that is Al, aluminum, which always has a +3. Zinc always has a +2. Silver always has a +1, and CD, cadmium, always has a +2. So there you go. There are 16 elements, specifically metals, that have fixed oxidation numbers, okay? That tells you that everybody else, all the other metals, have a variable charge. And we have to use what are Roman numerals to distinguish which one we're working with. For example, copper, right here, copper there's 2 types of copper. Copper is number 29, okay? Copper can be in 2 states, oxidation states. Copper can be in the 0 oxidation state, obviously, because when it's an element, but it can lose 1 electron. And when it loses 1 electron, it has a +1 oxidation state, or it can lose a +2. Okay, notice it, unlike the A elements, the main metals, we cannot predict what the oxidation number is for the other metals. And we have to distinguish the two by using Roman numerals. So a copper 1 + 1 will be designated. Let me clear this up here a little bit. A copper, there's 2 forms, copper 0, which has a Cu symbol, and it has a 0 oxidation state. Or we can be copper 1, oxidation state +1, or copper oxidation state +2, okay? To distinguish the 2 ions, we use Roman numerals, capital Roman numerals. So copper, Roman numeral 1, or copper Roman numeral 2, 2 complete different compounds. One of them has, in solid form, has a kind of bluish green color. That's the color that you may see a lot on copper, a piece of copper that has they call it a pantene, it's a green color. And then the other one has a very blue, very bright color, blue color solution, okay? So, and we use the Roman numerals to distinguish which one. There was a time when they used the terms cupric and cuprous, and totally ambiguous, because that could be, it was like confusing, because which one is the ick and which one is us. So what happened is we're using what are called IUPAC. It's a union, international union, that has agreed that this organization will name the compounds and name the format for all chemicals, so throughout the world, so everybody is in the same page. There's no ambiguity with respect to naming them, because it can be quite ambiguous. All right, so some of these variables can be like I say, copper is a +1, +2, but some could be, it can vary from a +1 state to a +9 state, depending on the metal, okay? Now, as we stated again, metals want to lose electrons to become cations, having an oxidation state of A+. We talked at length about the main elements, the A elements, the metal specifically, that group 1A will always have a +1 oxidation state and group 2A always have a +2. The group 3 metals always have a +3, and cadmium and zinc have always a +2, silver always a +1. Okay, now why is that important with respect to those that have an exact, if you will, oxidation state? And that is because when we're going to start learning about prefixes, we're familiar with carbon dioxide. That's the prefix, the dioxide. They're talking about 2 oxides. In ionic compounds, we don't use prefixes. So you can have magnesium chloride, which is MgCl2. It's not magnesium dichloride. It's simply magnesium chloride. Covalent compounds will use prefixes. So we will have carbon dioxide versus carbon monoxide. Okay. All right. No prefixes for ionic compounds. Prefixes for covalent compounds. Okay. So here, all the other metals, excluding the 16, will have an oxidation, can have an oxidation state of a +1 to a +9. Okay. And as stated earlier, with the other ones, we use Roman numerals. Okay. Roman numerals. Now we know about nonmetals are going to gain electrons simply because their stability is to become isoelectronic as the noble gas in front of it. So they're going to pick up electrons. And group 5A will always pick up 3 electrons. Okay. Also, the nonmetals, we change their name. So nitrogen becomes nitride. Okay. Group 6, like an oxygen, when they pick up 2 electrons, they become oxide, name-wise. Okay. Group 7, fluorine, chlorine, iodine, we get rid of the INE at the end and add IDE, and all of them have a -1 charge. Okay. And obviously the noble gases have an oxidation state of 0 because their octet is happy. It's not going to gain or lose those electrons. It's going to be very tough to do that. And helium obviously has a duet rule. Okay. Now we're going to take ionic compounds, and which is a combination of a metal and non-metal. And we're going to begin learning the formulas, and then we're going to talk about the naming of ionic compounds. Okay. Now remember that ionic compounds are made up of ions, cations and anions. Okay, with a specific charge. When we put them together to make the compound, the thing to remember is this: we must have sufficient cations and sufficient anions, so the whole molecule is equal to 0. Okay, and right now I want to use this general formula, what the formula we're given, but I'm going to give you at a later date a more specific formula to use that you can use for all conditions. So right now we have the number of cations plus the number of anions must equal 0 when we have put them together. Okay. All right. That's the thing, what is being stated up here. Now, in my scenario, what I'm saying is the alternative here, instead of saying 0, because most of the chemicals we're working with have a net 0, but there are some that have like the polyatomic ions may have a -1 charge, the whole molecule. And so instead of adding 0, I would just add the total charge of the compound, CP and compound, because it could be 0, the total charge could be 0, or it could be like the polyatomic ion, a -2. And I'll use some examples to help you figure out the oxidation number, because here's what's going to happen. When we start putting compounds together, initially you're going to know the oxidation number of both the cation and the anion, because they're going to come from they're going to have exact numbers. But there are times when you don't know what the oxidation state is, let's say the cation, because it could be a variable charge. It could be like copper. It could be a +1 or a +2. But you always will know, in that scenario, the oxidation state of the partner, the anion. You'll always know one or the other, plus the total charge of the molecule. And so like a real simple algebraic equation will allow you to calculate what that charge oxidation number is of the one that you don't know, okay? Unless it's fixed, and if it's fixed, then you know what it is. Now, clear this up. These polyatomic ions, we're going to use a lot when we are in this nomenclature as far as chapter dealing, as far as putting them together. The takeaway from this is this. Remember, these polyatomic units come as a packet. We don't separate them. If for whatever reason we need more than one, let's say nitrate, and then, well, what we do is we put a parentheses around it, and we do a subscript X, where X is greater than 1. If it's 1, you only need 1 nitrate, then you don't need a parentheses. But if you need 2 or more, then we put a parenthesis to show you how many of these nitrate ions you need, okay? Keeping in mind that each nitrate ion has a -1. And so if I needed to combine it with a cation that has, let's say, +2, then I gotta add 2 of the nitrate ions, okay? And therefore I will use a parentheses. We don't separate them. The other takeaway here to remember is these polyatomic ions have a specific name. We don't change that name to nitrogen trioxide or anything like that, okay? Its name is nitrate. That's it, nitrate. Then we get the nitrite and so forth. All right, so the names don't change. And if we need to add more than one, we put a parentheses around the polyatomic ion with a subscript to designate how many we need that are more than 1. All right, so they are a, oh, okay. They are a single entity and a unit. Compounds, when we start writing formulas, we need to bring them such that we have sufficient cations and anions so they cancel each other out, okay, to end up with 0. Now, let's say, for example, we're going to combine the elements sodium and nitrogen. So you may be given, make a formula for sodium and nitrogen. So what you got to do is we have to convert those neutral elements into ions. And we know that sodium is in group 1, so therefore it would have a +1. So we can write Na+1, okay? Nitrogen is in group 5, Roman numeral V, 5A, and when it becomes an anion, it will pick up 3 electrons. So its charge, its oxidation number is a -3, okay? And so we need to combine the sodium ion with the nitride. Remember, the nitrogen became name-wise nitride. So you keep that in mind, because you may need to name it. Maybe that's what we're doing. That may be the question. All right, so we need to put the sodium ion and nitride together such that we end up with a net zero. So I need 3 sodium ions for every nitride that I put together. Why? Because each sodium is a +1. I need 3 to cancel the -3 of the nitride. So this 3 right here becomes the subscript of the formula when I write it together. So the formula for sodium nitride would be Na subscript 3N. Okay? You see how that works? And if we were to name this, then we would say sodium nitride, not nitrogen, because we are putting the nitride together with the sodium. And that's just for sodium. But keep in mind, as we progress with this chapter, that we can do a lot of mix and match. We just use sodium here, but you can use any metal. Everybody, hello?
I'm sorry, I had to ask a question really quick. So, on the nitrogen, so if that was a 2 up there, then you would have only needed 2, right?
That would be correct.
Okay. And then would that have been sodium dioxide?
Well, let's say it was
Dioxide?
let's say it's oxide, sodium oxide. That's a -2, right?
Okay, yeah.
And we're going to combine it with sodium that we know has a +1, like we just did here. So that means I need 2 sodiums to cancel the -2 of the oxide. Remember this, its name now, the anion for oxygen is now oxide. So that 2 becomes the superscript on sodium. So that is the formula right there. And therefore its name is sodium. Notice that the metal name doesn't change, it's just sodium, but the non-metal name changes and that becomes oxide. Okay?
Got it, thank you.
Okay, no problem. All right, we're going to do some more examples here. And in here, notice like I stated, you can do this with all of the ions in group 1. Keep it simple like this for right now. We got lithium, sodium, potassium, rubidium, cesium, etc. So already you're starting to build up a database of these compounds that you're going to start putting together. And then you can easily move over to the next column because we know that calcium is a +2, right? And we go ahead and continue with the oxide, and the oxide is a -2. So when I put these together, I simply put, because the +2 cancels out the -2 of the oxide. So it's a simple 1-to-1. Its formula is simply a CaO. Its name would be calcium oxide. Okay, we could have hooked it up with the nitride or the fluorine or the bromide, chloride, what else? Phosphide, sulfide. Okay, see how we're building up our database? All right, let's continue some more examples. Excuse me. All right, question here is, what is the formula? So you may be given, like the previous example, you're given the elements, okay? And that's simply sodium and sulfur, okay? We would need to write a formula for these two. So as we just did, is we need to convert the element into ionic form. So sodium obviously remains the same as N +1. And sulfur, which is in group 6, okay, group 6A, when it becomes an oxidation number changes to a -2 because it picked up 2 electrons. It's a nonmetal, okay? It's striving to get the octet. So similar exercise, that shows me that I need 2 sodiums for every sulfide. And therefore our formula becomes Na2S. Name, I'll write the names down here in a moment, but this is called sodium sulfide. Notice at this point, for the previous example, sodium nitride, sodium sulfide, I have not used the Roman numerals I talked about. And why is that? That's because sodium is one of the sweet 16. Okay, I call it the sweet 16. Those are the metals that have an exact oxidation number. Sodium has a +1. Everybody has a +1 in group 1A. So therefore, since it's exact, we don't need to tell it the Roman numeral 1. And we know it's already Roman numeral 1, so that is eliminated, okay? All right, let's do this one. We have magnesium and oxygen. We go to find the magnesium, find out where it's at in the periodic table. It's a metal, it will lose an electron. Its new oxidation state is a +2. Okay, magnesium is number 12. Oxygen, like sulfur, becomes a -2. It's a nonmetal. And so therefore, we can very quickly simply put them together 1 to 1 because I got a +2 and a -2. So its formula would be that. You don't have to put a super subscript 1. It's understood, obviously, that there's a 1, okay? The only time you need a subscript is when you need more than 1. Again, magnesium oxide, because magnesium is one of the 16. Okay, I'll come back and get the names here in a second. Potassium is in group 1A and therefore has a +1 oxidation number. Phosphorus is in group 5 and it becomes phosphide with a -3 charge. Okay? Now, that means that it will have requires 3 potassiums for every phosphide. So now its formula is K3P. Now notice as we're going along, you can do the mix and match thing. We did the first one, sodium. I can mix it up with oxide. Now I can mix it up with phosphide. The same is true with magnesium and potassium. Mix and match. You start filling up your database of compounds. There is another tool. I'll go back to the course website that I put for you so you can practice naming and writing the formulas. You can do flashcards. So click on that. The name escapes me here real quick. It is called, where do you go? I don't know why it's not on yours. I need to find that out. I'll find out and get it corrected. But it's basically an additional resource for you. But in this case, it deals with nomenclature and naming. All right, so that's that one. Now, a little bit more of a challenge here. Let me clear up my mess here. We have calcium and nitrogen. So step number 1, break them down into the ions. Calcium is a group 2A, so it has a +2. Nitrogen, group 5. So it will have a -3, okay? -3. Now, the previous examples, I just added more cations to balance it out, or I put them together in 1 to 1. Here, I got a +2 calcium and a -3 nitrite. I cannot put them together simply as a simple 1 to 1 relationship, okay? Putting them together as follows would be incorrect because I got a +3, which doesn't cancel out the +2. So I got to put them together with sufficient number so they cancel each other out. But it makes it kind of challenging, but it isn't. I want you to think about this for a second. If you're doing mathematically equation, what do you call fractions, and I needed to add them together, and let's say I needed to add 1/4 + 1/5, can I add them just the way they're written? 1/4 + 1/5?
No.
No, what is it that I need?
A common denominator?
A common denominator, exactly. Now, if you look at these right here, I can't put them 1-to-1, but I do the same thing. I need a common denominator. And normally in this scenario, I just simply, I can use, for simple fractions, I can simply multiply the denominators, and I got my common denominator, right? Well, same scenario here. So my common factor between the +2 and the +6 is, excuse me, and the -3 is 6, is what I meant to say. That's my common factor. So I need to add enough calciums to give me a +6. So if I need 3, right? 3 times +2 is a +6. And I need 2 nitrides because 2 times -3 is a -6. Do I not have a +6 minus a -6, and isn't that equal to 0? Yes, it is. A lot of times you're going to see that when you get two charges that don't match up, find a common factor between the two. Okay. All right. So with that, let me erase some of this junk here. Writing that out as I did, that tells me that I need 3 calcium, it's a subscript 3, and 2 nitrates. And so my formula would be as follows, okay? Now, check this out. You didn't hear it here in this class, but I'm gonna help you out here. If you carefully look at the charge or the oxidation number of the nitride, doesn't that become the subscript of the cation? Yeah. And if you look at the oxidation state of the calcium ion, doesn't that become the subscript of the anion? Sure, no. Okay. So very quickly you can cross, but if you don't see that, don't worry about it. Find your common factor here, and then add enough of each ion to reach a common factor, and then that becomes a subscript, and that's your formula. All right, here we have another one where we have aluminum. So we know aluminum is a +3 metal, always will have a +3 charge as part of the 16. In fact, everybody here, all the metals are part of the 16, therefore the final name will not have a Roman numeral. The chlorides, the chlorine is in group 7, and it becomes a -1, okay? We need 3 of them, 30 chlorides for every aluminum, because aluminum has a +3. Therefore, our formula for aluminum chloride will be AlCl subscript 3. Okay, so I'm hoping you can pick up a little trend here to help you figure out, because let's say you didn't know what aluminum was and that's your formula, but you know that the chlorides will always be a -1. That means that the aluminum must be a +3 in the way this was written, okay? And vice versa. Maybe I forgot what the phosphide oxidation number was, but I do know that the potassium always has a +1, right? And therefore I got 3 of them. That infers that the phosphorus or phosphide must have a -3, because I got to put them enough of each so that equals 0. All the molecules we've written so far are neutral. They come from charged ions, positive and negatives, but we had enough of them, so when we put them together, they have a net 0 overall molecule-wise. Okay, the zinc is a +2. Okay, always a +2, and the iodide, like in the chlorides, always a -1. In this scenario, I need 2 iodides for every zinc, so that 2 becomes a subscript. So the formula for zinc iodide is Zni subscript 2. All right, let me clear some of this up. All right, now we have the variable oxidation number metals, copper. As I spoke earlier, copper can be 1 or 2 oxidation states. So you have to be told which one you're working with. In this scenario, you are working with copper 2. That Roman numeral right here pertains to the charge, the oxidation number of copper. So that tells you you are working with copper +2. Oxygen, like we did up here, will always have a -2 oxide. So in this scenario, okay, we have a 1-to-1 relationship, so we can simply put them together as a 1-to-1. Okay, so its formula would be as follows. Now let me add something else. Still with copper, I could give you this formula Cu2O, and think about this. What would be the oxidation state of this copper? What would you calculate it to be, given what you learned so far, as I put them together? Okay, because so far we know that the oxidation state of the oxide is always a -2, right? So what does that infer? That what is the oxidation state of this copper in this form? Anybody want to take a guess? Don't guess. Hopefully you know exactly. Remember over here, we needed 3 potassiums for every phosphide. If we know that the oxide is a -2, what does that mean that every copper in this format must be?
2.
A 2?
No, Gary came down and did this.
I'm sorry, you broke up, it had echo.
A 2, yes, right?
Yeah, but there's 2 already.
Oh, wait a minute.
Yeah, if there's 2 coppers right now already in this formula, what must each one be charge-wise, oxidation-wise, to cancel the -2 of the oxide?
+2?
No.
Okay, I'm lost then.
Okay, +1. Okay, if each one of these is a +1 and I got 2 of them, doesn't that equal to a +2?
I thought I just said +2.
No, but I was saying, what is each one? What is the oxidation state of each copper? Over here is a +2, no question there. But in this format, when we have 2 coppers, that means that each one must be a +1. Clear as mud? Let me redraw this, okay? Now, does everybody agree that the copper we just did is a +2, right? Because it told us right here, that Roman numeral tells you you're working with copper +2. But let's say you weren't given these ions. Let's say you were given this formula, Cu2O, and you're asked, okay, so what is the oxidation state of this form of copper? Keep in mind that there are 2 of them in this formula. Compare over here, this one, there's only 1. Okay? The thing they both have in common that the oxide each have a -2. And they have to equal 0 when they're combined. So this means that I have 2 and each one must be a +1. Okay, so that means each one must be a +1 because I got 2 of them. It's given to me here. So I'm working with copper Roman numeral 1. In this case, I'm working with copper Roman numeral 1. Okay, does that make sense? But now we got some more of those coming up, okay? to help out, because sometimes that's where the confusion sets in. What does a Roman numeral mean and who's it applied to? Remember, you see a Roman numeral in this scenario, it applies to the metal. The Roman numeral always applies to the metal that you're utilizing, right there. Always, never applies to the non-metal. Okay, take a look at this one here. Here they're telling you lead Roman numeral 4. That means that you are working with lead Pb plus 4. Okay, and the oxygen or the oxide is still the same. Nothing's changed there. So I put them both into ionic form, and then I gotta add enough of each so they cancel out. So that means I need 2 oxides. So my formula would be PbO2. Okay. Now with respect to the name, let's go back and do the names real quick. We have sodium oxide. Okay. Magnesium oxide. Remember that the oxygen goes from oxygen to oxide.
So really quick.
Yeah, go ahead.
Before you tell me the names, just so I can make sure I get this. So on a PB4 and oxygen, the reason why you need 2 oxygens to cancel out the 4 is because oxygen is a -2 charge.
You got it.
Okay.
Okay, you got to add enough negatives to cancel out the positives. So sometimes you don't add any more positive. You just need to add, in this case, they're negative, or vice versa. Sometimes like the number 3. Number 3, each potassium had a +1. So I needed to add 3 potassiums to cancel the -3 of the phosphide. Okay, so you're going to add one or the other. Now, in the case of number 4, I had to find a common denominator, which was 6. So I needed to add 3 calcium, which each one has a +3. And I needed to add 2 nitrides because each one's a -3. So it gives me a total of +6 and a -6, which equals 0 when I put them together. Okay, that makes sense? All
Yes.
right. All right, so number 3 name-wise would be potassium phosphide. Not phosphorus, but phosphide. Calcium nitride. Aluminum chloride. I'm writing very quickly, so hopefully you can write your notes a little bit neater than mine. Okay, zinc iodide. Okay, now notice in the first 6 examples with respect to names, no Roman numerals, because all the metals in those first 6 examples have exact oxidation numbers. Okay, and we know 100% of the time what their oxidation, they don't have more than one oxidation number, they only have one. Therefore, no Roman numerals. 7 and 8, however, you have to be specific. So you say copper, you maintain the Roman numeral, we were given Roman numeral 2, oxide. Compared to the one I was showing you earlier, this would be copper, Roman numeral 1, oxide. 2 complete different compounds, different properties, different animals, okay? And in the past, they used to use the term cupric and cuprous. In fact, you might find it in labels, food labels, or labels in general, describing what's in the ingredients. You will find that sometimes they still use the old naming compounds. Cupric and cuprous was very ambiguous. Here, there's no question about it. Roman numeral tells you the exact charge of the metal. And then here, the last one, we got lead, Roman numeral 4 oxide. Okay. All right, now, just with these 8, we went specifically with, like number 1, sodium, but keep in mind, you can take that sodium and combine it with oxide. Sodium with the phosphide, sodium with the nitride, sodium with the chloride, sodium with the iodide, and we already did oxide. The same is true with magnesium, magnesium sulfide, magnesium phosphide, etc., etc. And so your database of naming the compounds by just moving things around is building up, probably up to maybe, I don't know, 500, 600, 700 compounds, because you have all those metals on the periodic table. At least the 16 that you have, you can use the 16 with all the anions. And that includes, we're going to talk about the polyatomic ions from the polyatomic table. Okay. Now we're giving you a lot of examples, but it doesn't come near to what's out there in the world, so to speak. Tons of chemical compounds. All right, so with respect to this, it's important that you check the charges every time you put together a metal and a non-metal. Okay. Now, earlier I said that you use the total number of cations plus the total number of anions equals 0. Recall that. Okay, so number of cations plus the number of anions equals 0. And then I added something. I said, well, I'll make it the charge of the compound, which could be 0, or it could be a polyatomic ion. For example, we have NO2 -1. Okay, that's a nitrate. Oh, NO3. I want to keep it. I meant nitrate, and I wrote down nitrite. Okay. Now, and there are some homework problems where you're given polyatomic ions and they're asking you to figure out the oxidation state of one of them, one of the atoms in there. Okay. Now, when here, nitrogen is a central atom. Remember Lewis dot structures, it's a central atom. So it's not by itself anymore like the nitride. So it has a total different oxidation state because it's bonded to the oxygens. Okay, and you might be asked, okay, what is the oxidation state of this nitrogen? Well, using that general formula, I can say that the nitrogens plus, what else do I know? Well, the oxygens, which are oxides, have a -2, and there's 3 of them. Okay, so I got a total -6 there due to the oxygens. All right, so I got total -6. And the overall molecule has a -1 charge. Okay, so I got a real simple algebraic equation here. I got N plus a -6 is equal to a -1. Here's the charge up there. Rearrange and solve for N. So I got N is equal to 7 minus 1, which is equal to a +6. So under these conditions, nitrogen has an oxidation state of a +6. And this is what I mean about I may not know what that oxidation state of the partner is, but I always should know one or the other, either the partner or was bonded, the central atom or was bonded to the central atom, and the overall charge, okay? So I think this general equation just covers a lot more, gives you a lot more ways to calculate the oxidation state of species, whatever, whether it's an overall zero or has a specific charge, like the polyatomic ions. And like I stated, there are some problems in the homework. There are hypothetical formulas, compounds, and they want you to calculate what the oxidation state is for these hypothetical atoms, okay? You might get, in general, 100% of the time, you should get a positive, a whole number, but the hypothetical examples are, it's possible to get quarter charges, okay? Just keep that in mind when you're looking at the homework. Okay, now, here we're dealing with the polyatomic ions. We're going to combine magnesium and OH, which, if you look that up on the table, zoom it up a little bit. OH negative is down here. There's the formula, and there's its name, hydroxide. Okay, hydroxide. Well, hydroxide is used quite a bit in a number of things. If you have if you have acid reflux problems, you're drinking a lot of hydroxide. All right, so we got magnesium hydroxide, and they want you to write the formula. Well, they gave you the element Mg. Well, we need, as we did before, we need to figure out its oxidation state as an ion. We know that is in group 2A, so it has a negative, +2 charge. The OH is given to you, OH negative, okay? We need 2 of the OHs, the hydroxides, for every +2 charge of the magnesium ion. Now, that 2 now becomes the subscript in the parentheses. Whenever we need more than 1 polyatomic ion, we use parentheses. So that is the formula for magnesium hydroxide. Okay, remember that whenever you need more than one polyatomic ion, you put a parenthesis subscript. If you only need 1, don't use a parenthesis. Okay, we'll come back to the name of these. Okay, there's the formula. All right, kind of a little bit more challenging, but still, we take it, it's not too bad, okay? Potassium, we did a potassium earlier. We know that's a +1, okay? This is PO4 -3. Well, go look that up in the polyatomic ion, and you will see it. It is called phosphate, not phosphide. The IDE, here's a little trick to remember. The IDE ending tells you you're dealing with one monatomic element. So chloride is just the chloride. Phosphide is just the phosphorus. Phosphate means I got the phosphorus, but it's bonded to oxygen. And then there's phosphite, which is I still got the phosphorus, but I got less oxygen bonded to it, okay? All right, almost done here. So we need 3 K pluses. Why? Because the phosphates have a -3 charge, and we need 3 pluses to cancel the -3 of the phosphate. So its formula would be as follows: potassium phosphate. This one here, silver, we need to block that, set it into ionic form, which we know is a +1, always 100% of the time, +1. The sulfate has a -2, so that means we're going to use 2 chloride cations. So its formula would be as follows: two silvers, and then the SO4. You'll find that SO4 quite common in a lot of foods that we eat, sodium sulfate. Okay, let me clear here. All right. Calcium, group 2A element, so it has a +2. And then we got the nitrate, the -1 charge. I need 2 -1s for every calcium +2 ion. So its formula becomes as follows. Since I need 2 nitrates, I need the parentheses. All right, now we have the Roman numerals. We're dealing with copper +2. Why? How do we know that? Because they gave it to us in Roman numeral. That tells me that I have a copper +2. I'm going to put it together with CO3 - 2, which is a carbonate ion. It's a polyatomic ion, carbonate. I can, since it's a -2, excuse me, and the copper is a +2, guess what? I just need to put them together on a 1-to-1 basis. And there I go. If that were copper 1, given to you like, excuse me, as follows, then in that case, the formula would be 2, I need 2 copper, 1, and the carbonates, just like that. Okay, so copper 2 carbonate and copper 1 carbonate, 2 distinct different compounds. Okay, so the takeaway here is to remember to use the parentheses for the polyatomic ions if you need to need more than 1. Okay. Also, the takeaway here is you don't change the name of the polyatomic ions. The names are given to you, and that is the name of the polyatomic ion. Therefore, the first one would be magnesium hydroxide. Okay, not hydrogen oxygen or hydrogen oxide or anything. It's hydroxide. Okay. Second one, potassium phosphate. Also found in a lot of foods, by the way. Then we have silver sulfate. Okay. Then we got calcium nitrate. Okay, notice no Roman numerals because the metals are all from the sweet 16 and have exact oxidation numbers. Here, we're told copper 2 to use that. So its name would be copper, Roman numeral 2, carbonate. Now, when you put the Roman numerals, it does make a difference if there's no space after, in this case, after the last letter of the word, in this case, copper. If you write it with no space or with a space and Canvas marks it wrong, let me know and I'll get it fixed, because we're trying to teach, Canvas is definitely not AI technology. So it doesn't recognize that it's a space. It just looks for an exact match to the answer and doesn't account for spacing. So and that goes for any of the homeworks or whatever you do, if you just add a space or by inadvertently, hit a period, add a period, or even a space after what you wrote it, and it counts it wrong, let me know and I definitely will get it corrected. Okay. So also here, mix and match. Okay. You can now do a variety of mixing and matching, because now you got magnesium phosphate, magnesium sulfate, magnesium nitrate, magnesium carbonate, copper 2 hydroxide, copper 2 phosphate, copper 2 sulfate, copper 2, et cetera, et cetera, et cetera. Okay, so you get your database is really, really getting bigger. All right, so I've been giving you the names because the scenario is going to be this. You're either going to be given the name and asked to write the formula, or you'll be given the formula and asked to write the name. Okay, so you need to be able to go in both directions here. For ionic compounds, the name depends on whether the metal has a fixed or a variable charge. And like I mentioned, I already pointed out to you, the ones have a fixed charge, no Roman numerals. That means everybody else uses a Roman numeral. Okay. Let's get some examples. Okay, well, we know about the nonmetal. Its name goes from INE to IDE. So in this case, sodium chloride, good old table salt. Okay. Now let's take a look at this. We have K, which is potassium, and Br, which is bromine, but it is bonded to potassium. Okay, so therefore its name is potassium bromide. Okay, we have Mg, which is magnesium, and now we have oxygen, which is now ionic, becomes oxide. Now the term for oxygen, be it ionic compound or being bonded to a covalent compound, remains oxide, okay? So this is magnesium oxide, and if we were doing, which we will do some examples here in a second, this is carbon dioxide, still oxide. So the oxygen, the sulfurs, and the anion part, if you will, the nonmetal part, its name gets changed regardless if it's in ionic form or covalent form. Okay, so oxide is oxide, carbon dioxide. See that? The only difference is that di, and that's because it's a covalent compound. Okay, we got this one, calcium and fluorine. Okay, and you might think, oh, this is diatomic fluorine. No, it's not, even though it's a subscript to. This is bonded to calcium. See, we got written first calcium, and then immediately following that is F, which we would think, and then there's a 2, we would think fluorine, but it's not. The fact that there's metal first, then the halogen tells you this is calcium fluoride. Okay, note the difference. If it was diatomic, F2, there's nothing before it. That would be fluorine. Okay, but if you got a metal there, and 99% of the time, if you notice the trend, the metal is written first, followed by the non-metal. It can change around, but that's the format. Metal first, followed by the non-metals. Okay, so we got calcium fluoride. All right, we got Li, which is lithium, and then we got the sulfur, which now is sulfide because it's in ionic form. Okay, so this is lithium sulfide. And then we got Ag, which is silver. Okay, and then Cl, which was chlorine, but now became chloride in ionic form. So silver chloride. All right, so point here, take another takeaway, with ionic compounds and no prefixes. And so it would be incorrect to say calcium difluoride. That would be incorrect. Or dilithium sulfide. That would be incorrect. Unless you're in Star Trek and you got dilithium crystals, okay? Little side note there. Okay, let's see, we're almost done. Here's my time. Well, let me tell you what, we only got about 3 minutes left. Why don't I just stop it there? And we will continue next on Thursday. And we'll stop it on slide 14. Okay.